Thank you very much, Derek. Thanks a lot, Derek. I'm from Waterloo in Canada, and also we have collaboration in Bilbao in Spain. About 80% of our time in our lab is devoted actually to coupling between quantum and continuum models, but that's not what I'm going to talk about today. Apparently, there are many problems in biology which could be formulated, in a very simple way, but there are many difficulties there when we are talking about coupling, when we are talking about multiscaling and multiphysics. And that's what I would like kind of to highlight here, during this talk. So let's keep overview. So what I'm going to talk about thermal ablation. This is technology that has been around for a long time. And there are different modes for this technology. So basically what you do in most cases, you apply locally extreme temperature to induce irreversible cell injury. Because, for example, if you would like to treat cancer or other diseases, that's basically the way to go. But also there are other modes for that. For example, you could use lower temperature as well. I'm not going to talk about lower temperature. However, if you're talking about thermal ablations, there are, again, within this kind of big group of therapies, there are subgroups. One of them is radiofrequency ablation, and the other one, for example, is microwave ablation. And now, of course, is popular laser ablation as well. So let's see basically at radiofrequency ablation first. So as I said, the problem formulation is extremely simple because basically what you do, you apply electrode, right? You have grounding pads, of course. You have image guiding device for surgeon, for example. And you have some targeting biological tissue here. And of course, for radiofrequency, you have power generation. So that's basically what you have on the surface. So strictly speaking, I mean, if you looked for the first time at a problem like this, you look, hey, I could do pretty well this microscopic model. Well, as I said, it's kind of deceiving because, again, on the surface, if this is kind of also highlighted, similarly on the surface, you could look at the problems like this as microscopic model. However, what you have to do, you have actually, because what you are targeting in the end of the day, you would like your cell membrane collapsing, those damaged cells, you would like to collapse in them. And if you'd like to do that, you have to account many microscopic properties, for example, protein denaturation, enzyme function, and so on and so forth. So basically, if you look a little bit deeper into the problem, you will clearly see that basically what you have to do, you have to couple macro and micro level when you would like to talk about thermal ablation. Other thing is that, again, I mentioned the differentiation between radiofrequency ablation and microwave ablation. For radiofrequency ablation, there is additional complication here because there is always this so-called charring problem around radiofrequency electrodes. So basically, tissue just completely burned. And of course, you have to minimize that area too if you'd like to model that correctly. Let's kind of start from what basically we do and how we do this coupling. So what we do here, we develop coupled thermo electromechanical models for these thermal ablations of biological tissue. The starting point, you look first at the electromagnetic field. So you look at Maxwell equation. You don't need, for problems like this, neither for radiofrequency ablation nor for microwave ablation, complete set of Maxwell equations. Like, for example, if you look at microwave ablations, you have immediately simplification here, which kind of tells you that, okay, because the devices typically operate at one frequency, so transverse electric model is sufficient. So basically for electromagnetic field, you end up for microwave ablation with Helmholtz equation. If you look at radiofrequency ablation, so typical, it's lower frequency range in this frequency range, and further simplification can be made. So you end up basically to model your electromagnetic field with quasi-static electromagnetic approximation. And what is important here also to know that volumetric heat generation, basically, which you will see also entering the other equation at the next slide, is also important after you define your electric field. So typically, if you look at the literature, basically for many, many years, it has been modeled with Panner's bio-heat equation. And Panner's bio-heat equation, of course, is using kind of standard Fourier law, Remember, I was mentioning just on the previous slide this component QP, which volumetric heat generation, so it enters basically this model here as well. There are other components in this model. I think the next slide can actually highlight them. So this is electric power generation, metabolism source, blood perfusion, which is extremely important here too, and the standard part of this kind of Fourier type of equation. Now, what is important is here that, you know, kind of every time we are using parabolic equations, we have to be cautious. We have to be cautious because clearly this is infinite propagation of waves, and definitely there are some relaxation phenomena that have to be taken into account. It has been known for ages, but we still, even in computational fluid dynamics, we kind of, you know, cautiously just using those parabolic equations. For this type of problems, you cannot do that. You have to account for relaxation time effects. And as I said, this is something that has been known for a long, long time, since Cataneo-Vernot time, and even before that. And so what we did, we took into account basically this micro scale response in time using so-called the single phase lag model. But we also analyze a correction for our heat equation, bioheat Pennis equation, also using dual phase lag models as well. So basically, in the dual phase model, as name suggests, you have basically two relaxation times here. One is pretty much, is not pretty much, but the same as you would use in standard Cataneo-Vernot type of equations for hyperbolic correction of your parabolic equation. But the second one also is accounting for the time relaxation in establishing the temperature gradient. So that's basically what you have for that part. Now, for mechanical deformation part, again, on the surface, it's kind of standard because you have pretty much like, you know, phenomenological thermoelasticity type of connection here, except that you have two things here. You have thermal expansion, which is basically, of course, connected to your Pennis equation, but also you have to account for thermal shrinkage. Remember I was talking about this Charring phenomena and damage volume, which has to be minimized. So this is also quite essential part in this type of problems. And of course you have kind of wave equation, so thermoelasticity coupled to that Pennis equation in terms of biological tissue. Now, the other part of the picture, as I said at the beginning, is microscopic level. And microscopic level, it's because the reason because you are targeting your cells, you would like damaged cell to be collapsed. And so the simplest what you can come across is basically look at a three-state cell death model, which basically used to quantify the protein denaturation. So basically what you, like mathematically speaking, what you add up here to your coupled system of partial differential equations, you also use ordinary differential equations for the protein denaturation, which is responsible for that smaller scale level as well. And further, what is important, you may or may not remember that in bioheat equation there was this value psi, which is responsible for relative shrinkage. And this is, again, this is very important parameter, which again, from the microscopic level enter that macroscopic level of the equations that you've seen before. Now, again, you look at computational domain, what is difficult here? Like, for example, you've heard, you know, talks before, very complicated computational domain and things like that. Again, this is just on the surface because you put this electrode. In electrodes, there are different parts. There is insulated part, there is active part, there is fixed surface. And all this heterogeneity has to be taken into account. You look at the boundary condition. So you have a moving boundary, thermal insulation. You have, again, moving boundary here, and so on. So on the surface, the geometry itself simple. However, boundary conditions, heterogeneity add up to the problem complexity. Apart from the fact that, as you've seen, it is coupled multi-physics, multi-scale problem. So the first pictures basically that you would see here are related, for example, to the effect of thermal electromechanical coupling. And what we did here is the comparison of temperature profile, because this is the very first basic characteristics that you would look at. Depending on the position where you, from the slot center where you enter basically your electrodes to the blood tissue. Basically, again, what you see, this is visualization of the total displacement distributions of the couple. Again, this is done for microwave ablation here, this time progression. The situation here, basically, when comparison is made when you do coupling, as I described, as we did, or you don't do coupling. And of course, the closer to the slot area, the deviation is becoming more and more pronounced. The further away, no, it's not a problem. So basically, you could use those simplified models that other people use. But the closer to the slot area of electrodes, this is something that have to be accounted for. Now, the other thing, as I mentioned, these hyperbolic corrections of your parabolic type of equations for distribution of temperature, which is specifically in this field, like if you look at many applications in mechanical engineering or generally in engineering applications, it may not be the case. But looking at a number of biological applications, it is absolutely essential. So even the single phase, so basically here is represented temperature distribution, total displacement, damage volume. In all the situations, you would see that accounting for the relaxation time is important. If you look at this dual phase model, dual phase-like model that I was talking about and we are using in our, it's even more pronounced. So basically what is represented here, temperature, radial displacement, total displacement. This is fraction of cells in different states. Remember, this is 3-DES model. So native state, unfolded state, and denaturated state. And this is damage volume as well. So now I have just 5 minutes, and I just would like to mention that basically the techniques that we've developed is important, of course, for classical applications of thermal ablations, like for some cancer treatment. However, it's also extremely important, for example, for chronic pain management as well. And this is, we did also some initial works in this area. And the reason for that is very simple, because you look at this kind of standard medical therapies for chronic pain management, it's actually short-lived therapies. And this technique could allow you like 10, 12 months or even more, from 10 to 18 months. So basically more and more medical practitioners basically looking at that. And again, you look at the computational domain, similarly simple, however, again, heterogeneity here and other kind of, I just highlighted here, disparity between you know, different areas in computational domain that you have to account for, muscle, bone, nerves, and so on, including blood here. And yeah, I have just a few minutes, so I'm not going kind of, so the only important here, based on those couple of models that I described, you also calculate the ablation volume as a result. And here's the results as given already for radiofrequency ablation, depending on the distance. That's another characteristic that is extremely important, the distance between nerve that you are targeting and the bone itself. Depending on the distance, basically thermal performance, for example, will be quite substantially different. And this is, again, thermal distribution. This is other stuff. So this is thermal volume, and this is propagation of lesion volume. The point, remember, 50 degrees here, isotherm, is corresponding to this charring temperature, beyond which you should not go. What, 1 minute? No, Derek? 2 minutes. Conclusions, you know, all these characteristics that I already mentioned are quite important. The last 1 minute, I'm just going to spend on closely related things, which what I've just mentioned is basically model for continuous thermal ablation. However, quite popular nowadays in competing technology is pulsed thermal ablation. And there, basically, 2 additional characteristics that are coming into play is, of course, frequency and duration of your pulse. And this is something that, again, we started. And actually, the title of the preceding paper is exactly about that. So that's why I'm spending the least time for that, because you could actually read that. But this is a kind of effect of pulse duration and other things that as I said, you could have a more close look at the paper proceedings. So this is acknowledgement to our funding agency and also our supporter in Spain. Thank you very much.